Thank you for your introduction, Peter. Yes, I won't comment on it. This is basically what I'm going to be talking about. A little bit about carbon and stainless steels, because I'm sure lots of you know all about stainless steel, but I'm also sure that a significant number of you don't know quite some of the details. Then a bit about chloride limits, a bit about standards, a bit about practical issues, the reasons why people said that you couldn't use stainless steel reinforcement because it wasn't going to be any good, and then some applications, some of which you will be familiar with, some of which you may not. And let's start off with the nasty bits. This is Melbourne. This is what happens with concrete, marine environment. Hasn't got quite right. I've got no idea what the particular problems were. Probably the people who worked on fixing this do, but I'm not very interested. It's just an example. And just to be really dramatic about it, here's a nice bit of stainless steel. Here's a nice piece of carbon steel. And you can see what the difference is like. Or, pinched out of a Georgia Institute article, what happens when you have little problems with piles and basically spalling, things falling apart. So, okay, that's the issue. And people talk about, well, all right, what are we going to do about it? The reason why it's happening, we've seen this before in this session, and you've all obviously seen it before. You get your corrosion product, it gives spalling, cracks along like that, and eventually goes away. And the critical bit, from my simplistic point of view about concrete, is that once you actually get oxygen in, once you've got a crack, then you're on a road to perdition. You know, it's just going to keep going until it gets very bad. And the whole idea, from my point of view, is that, well, maybe you can do something about it by putting something in there which isn't going to cause that sort of large-scale oxides like this, and it isn't going to cause this large-scale cracking. So, the conventional view, you get damaged by carbonation, lower the pH, depassivates, or if we're talking Rob's version of it, you have a crack and you wash the alkalinity out, and that has the same effect. Chlorides get in and cause attack to the steel. Yep, nice, simple. You can control it, and that's what a lot of what we've been talking about, or other people have been talking about, changing the concrete, adding inhibitors, applying cathodic protection, all sorts of bits and pieces. I'm not going to talk about that at all. I suppose you could use metal fibres, and we haven't talked about that at all. You know, metal fibre, well, it's not really going to give you enough expansion to actually cause a crack, and the only little problem is that it probably won't also give you an awful lot of tensile strength unless you put an awful lot of it in. So typically, people are going to want to have some sort of rebar, give you some sort of decent strength, and hence, hey, my solution, stainless steel. Except it's not my solution, it's been around for a long while. Okay, the basic difference. There is a piece of carbon steel. Iron, controlled bit of carbon, put water on it, put corrosives on it, and what happens? You get some rust. And it just keeps going, because that accumulates rubbish, that accumulates the water, it accumulates the chlorides or whatever, and eventually you wind up with a lovely little pile like that. If you add 10.5% chromium, and hey, this isn't an Australian definition, it's an international definition decided by the customs people. If you've got 10.5% chromium, it's a stainless steel. You mightn't think it's a stainless steel, but it is. Equally, if you've got 9% of chromium, it is not a stainless steel. It's a high chrome alloy, and there are high chrome alloy reinforcements around in some of the standards too, but it's not a stainless steel. The critical bit about this is that you form this passive film. I am absolutely not going to attempt to tell you what's in that, because it's a very complicated chrome oxide, hydroxide, etc., etc. But the great thing about it is it forms very rapidly, milliseconds if it's damaged, comes back to about where it should be within 4 to 24 hours, depends on the conditions, and it will basically mean that the world doesn't see a stainless steel, it sees this protective layer. Great. That is the corrosion mechanism, sorry, the protection mechanism that you have for all stainless steels. So, there's chromium there, there may also be molybdenum there, and there's also going to be some nitrogen there. All of those will give you better corrosion resistance. The other things that are in there, the nickel, the manganese, oh, we've got the nitrogen already, what they do is just change the mechanical and physical properties. Now, nitrogen, nice tiny little atom that it is, gets a foot in both camps. So if you add lots of that, you get better corrosion resistance and you get the changes here, and I'll just talk about that in a moment because it's the difference between ferritic stainless steels and austenitic stainless steels and duplex stainless steels, just briefly. Okay, in case anybody is not going to ask the question, the reason why you've got to add these extra bits is you can't get beyond about 30% with that, you can't get beyond about 7% with that, you can't get beyond about 0.2 to 0.4% with that, and so that limits what you can do in terms of corrosion resistant with stainless steels. Mind you, if you add all of those to the top, then you've got an alloy that you just can't do, so we'll leave that out. Okay, that's the, yes, I've said that. All right, now this is a nice little picture of atoms cooling down, solidifying. It's very first year materials, I'd imagine. And you've got a beautiful body-centered cubic. All the iron atoms or the chromium atoms or whatever's there. If you add some nickel, and I'm sorry my animations went a bit screwy, that's a bit bigger. You can't fit it in there, so they all come out and they pop onto the surface. Your nice little face-centered cubic. Austenitic. You know what austenitics are like. They're easy to form. And it's just the structure. I mean, you push on the corner, it moves in. There's absolutely no bracing across, whereas there's lots of bracing here. And, okay, it's formable, it's tough because you push it and it recovers, and it's weldable. Doesn't matter so much at the moment, but really it's just a matter of all the rubbish atoms that are around when you weld are going to get hidden inside this cathedral of a hole, whereas there they can't fit in. They tend to crack when they squeeze into the gaps. Why is that important? Because I'm talking about the difference between ferritic stainless steels, which aren't very formable, and the austenitic ones, which 55%, something like that. All right, so what happens if you don't add enough? Well, you go from ferritic, you add 8% nickel, you get austenitic. If you only add about 5%, you get this duplex structure. And here you've got the ferritic composition there, the blue colour, and the austenitic grains here, which of course have been elongated out by rolling. So this is a duplex. Heaps of them around. Most of the reinforcement you get is going to be in these two. There is one standard at the moment, I'll talk about this in a minute, but there is one standard that permits you to have these and another one which is about to stop permitting you to have these, but most of them are going to be there. And these are the families. You know, the austenitics, the iron, chromium, nickel ones, the 300 series. You may find some 200 series around which are not terribly recognised. ASTM standards have formally got in some 200 series alloys, but you won't see them much here. Well, you won't see them here. And the duplexes have made a big run because they're strong. And this is just showing that. Here we've got structural stainless steel. We're looking at strength versus elongation, 20% or so, 50%, 55%. These things, they're quite nice. And the ferritic ones about half. The duplexes, about double the strength. So if you want lots of strength in a rebar, you may well look at going for a duplex, particularly for reasons I'll talk about in a bit. And the martensitics, no, not usually. Not much corrosion resistance either. So austenitics and duplex grades are the ones. Corrosion resistance. Well, I've talked about that. I've said chrome, moly, nitrogen. That gives you corrosion resistance. This gives you a thing called a pitting resistance equivalent. And you may well say, well, okay, how's that worked out? Well, the testing for this is done either in an acidic chloride solution or in a neutral chloride solution. So how's that relate to concrete? Well, it doesn't, not at all, because this is simply for grading stainless steels, not for grading stainless steels in concrete. We'll come back to that. This bit about PRE, if it's 40, is called super. Resist corrosion in seawater. Corrosion in seawater, 8, 8.2, 8.4. Not anything like concrete. But remember that people have talked about that's the alkalinity, or you may not remember, the bit where pieces of 316 were sticking out of OPC into seawater and they didn't corrode very much. And the alkalinity was talked about as the reason why that wasn't a problem. Maybe, maybe not, but that's the sum for grading. Corrosion resistance doesn't depend on whether it's a duplex or an austenitic or a ferritic, and it doesn't depend on the nickel content either. So low nickel, high nickel, really doesn't matter in terms of corrosion resistance. In these three families, the ferritic, austenitic and duplex, yep, you can get any mechanical properties you like, provided they fit in with that, but you can have exactly the same corrosion resistance. So you might get very high strength for the duplex, half the strength for the austenitic, and about the same strength for the ferritic. These two, it's a movable feast. Instead of heat treating the thing, like carbon steel, all you do is cold work it, and you can get a lot of strength out of cold working it. And I'll tell you now to note that if you put the pH up, then you will substantially reduce the risk of corrosion occurring for stainless steels. Exactly the same way as with carbon steels, and it's borne out by, you go look up corrosion tables, mixtures of sodium hydroxide, sodium chloride, and suddenly you find that stainless steel is just about invulnerable when you get way up in pH. Much the same as carbon steel would be. This is the example that everybody quotes. There's some beautiful, go and have a look on Google at where it is, because it really sticks straight out into a really aggressive environment. Why on earth the Danish government gave them their 220 tonnes of 304 back during the war, goodness knows. But okay, they built the thing. And when they ran out of capacity on this, they said, well, we'll build that one. And that was done in, 1970? This was done in 1940. And that was built with carbon steel rebar. And this picture was taken in 2006. And as you can see, the carbon steel didn't really stand up to it. This thing has suffered corrosion. If you read the Armanox report about it, it talks about pitting, it talks about some stress corrosion cracking, but it was still operating and is still operating. It's been extended out for 6 kilometres or so. So that is the longest history I know of stainless steel reinforcement used in chloride environments. And it's something that, well, it speaks for itself. Okay, so round about 2000, a bit before it, the Brits set up a Concrete Society committee and went back hunting. And they found quite a large amount of detail on work that had been done, and one of them was the one I was talking about, OPC in concrete, stuck in the sea, Oldfield and Flint. But they also found Italian work looking at all the various aspects of stainless steel in concrete, putting chloride in, looking at the properties of it, what might or might not, and there were a large number of examples scattered around the world of people who had used stainless steel very successfully. Then there was a surge in, well, during the 90s, early into the 2000s, where people were getting enthusiastic about using stainless steel, And in fact, some of the concrete industry got up and started beating the stainless steel industry around the head and saying, why aren't you promoting stainless steel? We've been promoting it all this time. And Graham Gedge at Arup was one of the ones who did a lot of that beating people around the head, I suppose would be the way of putting it. And it's gone on from there. Okay, so what were some of the reasons why people were saying you can't do it? Well, galvanic effects. Hey, you've got carbon steel, you've got stainless steel, you put them together, in the air they corrode, or wet in air and they corrode. And that's true. But putting it in concrete, enormous amount of work done by him and then lots of other people since, showing carbon steel, you only got about 25% of the macro cell current with stainless steel if you hooked it up to a good piece of carbon steel in concrete, in a simulated concrete, compared to what would happen if you had a piece of rusty carbon steel coupled to the same piece of ordinary carbon steel, which sort of knocks things on the head. The other bit about it is, go and have a look at the advanced corrosion notes, advanced corrosion course notes about real potentials, and you'll note that carbon steel in concrete is roughly the same potential as a piece of 304. So you don't have much in the way of a driving force. And the third thing is that stainless steel is a pretty awful cathode. All three of those contributing to this. Durability, this stuff that I talked about, done by a building research establishment in the UK, and basically showing that 316 in seawater would be okay if it was connected to concrete. Fine. I'll show you a slide in a minute, but we're talking 20,000 parts per million chloride in seawater. The typical 316 number in neutral environments is about 1,000 parts per million. Okay, thermal expansion. Okay, the thermal expansion of austenitics is about 45% more than carbon steel. For duplex, it's about 18% more. These are just the numbers. And therefore, what happens if the temperature changes? Is this going to be an issue? Well, maybe in the Middle East, but how much of length are you talking about if you're going to be putting stainless steel in for short lengths, selective insertion of it, compared to the carbon steel that's there? And I mean, inside a fairly lumpy piece of concrete, how much temperature change are you actually going to get? All right, I don't think that's an issue. And as far as I'm aware, I don't know of it being an issue ever and causing cracking. Ductility deflection, elongation at fracture, yes, austenitic a lot more than duplex, than ferritic, sort of 55, 35, 25, approximately the same percent at elongation, but the modulus of all of them is about 200 GPa, so that's going to be determining the deflection. Why is that an issue? I'll show you in a second. Oh, I'll do it now. Here is stress-strain curve, so load elongation if you wanted to be simplistic about it. And this is 350 grade, 250 grade carbon steel, fairly linear. So we've got an annealed piece of stainless steel. Yep, there is definitely going to be quite a difference in elongation for a certain amount of, elongation for a certain amount of stress. But if you've cold worked the thing, and let's face it, what do you do with a piece of stainless steel Rio? You cold work it to give it strength. So you're somewhere up one of these curves, and there really isn't the hell of a lot of difference in terms of the amount of deflection that you're going to get. Certainly if you start going out to 1% or so, it'll be different. But for the initial deflection, which is hopefully not going to be much more than you're doing, otherwise the concrete might not like it too much. Anyway, so from that point of view, I don't think that's an issue. Yep. And yeah, just filling in the details, 200 GPa initial slope, there's the 0.2%. Expense, well, if you're going to build everything out of stainless steel, all of the reinforcement, yes, sure, it would cost more. There's probably an argument to say that, well, it's actually probably not going to cost an awful lot more in the overall life if you're looking at not having to do any repairs on it, but that's not a good argument. The economical way is to put it in absolutely the places you need to put it in, and I'll talk about that right at the end. Then the other question is, well, can you get high strength stuff? And the answer is yes, you can. You can cold work austenitic stainless steels up to 800, 1000 MPa. But why bother? I mean, if you've got a duplex which is going to give you double the yield strength and commensurate greater ultimate strength, then why not do that? Really, it's only since the, 1970s that AOD has been come in, and so people could actually make duplex stainless steel. I mean, yes, the 329 versions of it were around since the 1930s, but you couldn't weld them, and they were, well, not all that useful from that point of view. But so large diameter bars, typically more than 20 millimetre, perhaps 25 millimetres, you would tend to go for a duplex and cut back down on the diameter. Show you a picture of the metallurgy of that a bit later. And bond strength. I'm not quite sure how this arose, but it seems to be something about the idea that, well, you're going to get a reaction with the carbon steel, or perhaps with the rust or the mill scale or something on the carbon steel, and that's going to give you a good bond. And stainless steel is bright and shiny, and so stainless steel just won't stick as well, so you won't have the bond strength. After all the people that got to do the work and say rubbish, garbage, just isn't true, I sort of wrote this down. I'm not exactly sure whether it's true, that's one of the reasons, that if you're looking at a pull-out test on a piece of deformed bar, then naturally you're going to be pulling against the deformations on the thing rather than a chemical bond to the actual reinforcement itself. Hey, this is just me being a simplistic materials person. Thermal expansion, well, I've talked about that already, so I'm not really worried about it, but let's just look at, and this is out of the EN standard, what the variation in thermal expansion coefficients are for the bits in concrete against the stainless steels. And we're talking typically the austenitics and the duplex, and concrete's going to be in the range 7.4 to 13, depending on what the particular mix here is. So apart from the fact, these numbers are for 0.4 to 0.6 water cement. Apart from the fact of, I don't see an issue in it in terms of sizes and so on and temperature changes, the whole thing is really a bit of a furphy. There is even, this is a comment, I can't remember where it was now, it's in the paper, a slight smoothing effect. So if you put some reinforcement in there, 2% reinforcement gives you a slight change in the thermal conductivity overall, but it's a second order effect. Why would anybody bother in being worried about that? This is out of the Italian work, and it is looking at chlorides versus pH, and this is why carbon steel gets away with it. This is why we can have carbon steel reinforcement. That's not the main reason I'm putting this up. The main reason is I want to point out just how big the area of stability of a relatively low level stainless steel is. 304, 304L, or the lean duplexes, the 2101 or even the 2304. So up to a couple of percent. And if you want to go a bit further, okay, 316, you're up to 3.5% chlorides. And these sorts of numbers have been, these sorts of numbers there, have been repeated and justified, and the whole conversions bit between, you know, cement, chloride and pH or hydroxide as against chloride to cement, as against chloride to concrete, starts getting really, really hairy. But hey, a very large range of stuff here. So if somebody says, well, okay, we're going to go putting things into seawater, and therefore we have to have duplex or super duplex reinforcement in it, I say unto you, why? Look at it. How much chloride are you actually going to get in there? The one circumstance in which I would say that you might need a higher alloy would be if your reinforcement is coming out of the concrete into the seawater and you then need to get something that would resist. So, yeah, okay, then you'll need something that's a PRE of 40. But it's not because it's in the concrete, it's because it's now in the seawater. And that's where our carbonation pentylethalin change comes. And as you can see, it's right past the end of where the carbon steel is corroding furiously. So if just because it has only just changed doesn't mean that the carbon steel is not in deep, deep doo-doo. This is the neutral bit. This is looking at neutral pH, levels of chloride, different stainless steels, and what, 10%, 1%. So 20,000 parts per million is here, and well and truly 316 is out of it. So you need the super alloys. So that's the counterpart to this graph. That's in the concrete. This is out of the concrete in whatever it is. Whoops, wrong thing. And at the same time, they did the similar experiment at 40 degrees C. The previous one was at 20 degrees C. Very similar shape, very sharp jump in these curves to be much more forgiving, I suppose is the word, once you're way out beyond 12.5 or so. So high passivity. And I'm not going to bother with that. This down here is just the numbers off the previous graph just for comparison. All right, so just to look at PRE versus chloride hydroxide ratio for a number of different things. Some of this is from, or some of this data is from American Highways research reports. Carbon steel, that's the chloride hydroxide. Yep, PRE naught. 9.3%, and the reason I'm putting that in is because of the 9% alloys that have been tried and are being used by some of the highways authorities. 4.9, and the PRE predicts it to be 9.5. So there's obviously a complete disconnect there. Clad 316, yep, 4.9. Okay, experimental work. And the problem is that if you look at that, it says, well, 24 for cladding and about naught if it's near defects. So clearly the defects, and there must have been defects, are overwhelming that. 2101, which is a lean duplex, 9.7, but the PRE is about 26. And 316 LN, greater than 20, and 26. So this is actually been pickled, so this is actually showing up reasonably the same sort of things. But there's a real, as I said before, a real disconnect between expecting a neutral or acidic chloride thing to predict what's going to happen with a highly alkaline environment. Yeah, I'm not going to deal with that. It's part of the argument about when you're using a cyclic ponding test and you're first feeding the solution into, and there's a standardised test, you're meant to use the same solution, but you really don't want the thing to be more than damp, less than damp, otherwise you suck stuff in and your initial surface concentration of chlorides just distort the whole test. Let's not get into that. There's people here who've done the tests themselves and know very well the precautions you've got to take to do those tests. Okay, so standards. Quite a nice standard, the British standard. nice glossy cover. There's an enormous amount of information in it. Well, it is. It's a beautiful glossy cover. It's nice, convenient, and it doesn't bend either. Standards tend to get destroyed by being dragged around. This is for use on the shop. It's got 8 types: 4 austenitics, 4 duplexes. Full stop. That's it. One of them's 4. Yeah, that's right, 4. Goes up to the 6% moly. Allows for the high duplexes, normal duplex, high duplex, so 4 of them, 4 of the others. You might note this end bit, because what tends to happen, or what does happen, is that always these standards are looking for the higher strength side. So they're talking either higher strength by N, and then they probably look at going for slightly higher corrosion resistance by putting in the 2.5% moly limit rather than the 2% moly limit, which is what we're used to here. There are 3 grades, and this is the engineer's bit that gets us poor materials scientists really confused, because grades means strength. The wire for wrapping the thing up, and then 500 and 650 MPAs. Other mechanical properties are specified in that, and it's really quite prescriptive. It's got very, very solid guidance on design and handling, and from that point of view it's an excellent piece of work. And it's got some normative electrochemical testing of corrosion resistance with bars using lollipops. I didn't know what they were called, but lollipops is good. And it links into the UK, now, what is it, English Highways? What's the name of the organisation now? Highways England, yeah, okay. It used to be Highways Authority back there. And the CARES Quality System Certification Inquiry, which is an essential part of the provision. I wish that we had it here. We tend to get an awful lot of rubbish out of a large country that will not be named. And the old code BA 8402, one of the things they had in there was silanes, but as I learnt yesterday, silanes came and went with barely a whimper. And they put out this little graph came out saying, okay, do some sort of stainless steel in here because you're going to get salt, splash zones, icing desalts, or, and I love this, I wish that it happened here, anywhere where repairs would cause unreasonable amounts of disruption. All right, USA. I'm not going to go all around the world. 955M. These are high manganese 200, and they're the only really big standards organisation which has got them in, and I think it's largely because of the highways people looking for alloys which were a bit cheaper, because the states were responsible for the... I'm doing that, aren't I? The states were responsible for looking after highway bridges, and they wanted something that was a bit cheaper. Mind you, they also pushed for 9% and said, maybe. But 304, 316, again, the N grade, and there's currently some discussions with inside ASTM, which you can't talk about because you're not allowed to talk about it until it's a standard, but at the end of it I wouldn't be at all surprised to find that there are more duplexes in there too. Currently, this standard allows all of the 40 types of alloy that are in A276, which includes martensitic, it includes ferritics, it includes precipitation hardening. Clearly, they're not going to get in there, and the reason why they're not going to get in there because there are some fairly stringent corrosion tests involved that they just wouldn't pass. There is another issue in that if you try and make deformed bar out of ferritic stainless steels, you may well wind up with cracks, which isn't all that good. Grades, 2 different grades, and the corrosion resistant, written into the standard, a means of qualifying other alloys is 60-week wet and dry ponding test, or a simulated pore solutions for, I think it's 15 weeks, looking at macrocell currents. So 2 layers of reinforcement and ponding for this one, or putting the thing into a simulated pore solution, basically. Standards and codes in the States also include the highways people, and I've mentioned this before, but again, looking for higher strengths. Now, this comes from goodness knows where. I'm sorry, I'm not good at referencing stuff. It's in the paper. Large diameters tend to be duplex because if you've got an austenitic, you tend to get a martensite-rich surface, and underneath you actually don't do a terribly good job in strain hardening it. And so by the time you get out to 20 millimetres-ish, it's easier to go to a duplex rather than to go to an austenitic. Quality issues. Heat tint. Hey, listen, it's going into concrete. It's not going to corrode. Why bother? Well, because it does matter. This is what happens. That's just heat tint, all right? This is what happens. If you have heat tint on and it's 304 and 316, and you're going from that sort of pitting resistance with more colour down to this sort of pitting resistance. This is about the level of 10, 11, perhaps even 12 chrome. So you've lost all that corrosion resistance. If it actually mattered. But hey, you're paying the money for the stuff, you may as well get the best advantage of it. This was an effect of weld tint and scale, and this was where the numbers came for the 25% that I talked about before. Here, you're looking at carbon steel to carbon steel corrosion rate. Here you're looking at 316L, and now let's think. C is carbon steel 3% connected to 316L, and that's there. These, with simulated welding oxide, the corrosion rate is enormously larger. So those two are talking about the welding oxide. This is talking about the difference between 304 and, stainless steel and carbon steel to carbon steel. And just the conversion factors. So 316 is a poor cathode, and I've talked about that before. Make sure you don't do that sort of thing, because it winds up like that, and you proceed to get pits and stuff all over your stainless steel. If you've ever looked at the Armanox things, or the Duranox and so on, dedicated tooling tied up with plastic, dedicated tooling again. This is from the Ontario DOT, their quality control inspection of reinforcement coming in. That's nicely pickled. That's a bit too, not quite properly pickled, but still acceptable. That's got stains on it from probably iron in the wash water, and this is just over pickled. And that would be what it would look like under pickled. This is a magnified image, of course. That's about right, so that would match up with A, or probably with B as well. And that is massively over pickled, and that's what that would look like. So relating the surface appearance at a micro level, this is just grains on the surface, to acceptability of corrosion resistance. Okay, whiz through a couple of examples. How am I going for time? Just about running out. Progresso pier, this is when both piers were there, so that's in 1969, that's 2014. And this is 2014. This was an environmental assessment. The Nickel Institute decided that they would get an assessment of the life cycle costing. And somewhere along the line, the people who were doing the job decided they would do an environmental impact assessment as well. It rather massively added to the cost of the job, but we wound up with these little graphs. And you're looking at acidification potential. Oh, and this is what just straight 304 reinforcement would do. This is what the, if you rebuilt the thing in carbon steel at the time, and therefore you've got to replace it once on the way through, this is what would happen. And obviously, building it in 304 was better, but it's not enormously better in terms of these environmental things, the global warming potential, the photochemical ozone creation thing, the primary energy demand, eutrophication potential. I had to look some of these up. How on earth is eutrophication going to be an issue for, but yeah, it makes sense. The reason why it isn't an enormous difference is because how much steel is actually in that pier? Not a lot. So if you actually look at the contributions, most of this comes from the concrete rather than from the steel. But even so, there is still an advantage. Oh, and in terms of the life cycle cost, it was about 40% cheaper going from when it was built through to 2020 to put it into stainless steel rather than carbon steel. Whoops, pointing the wrong way, pressing the wrong thing. This is a bridge in Switzerland, bridge that suffered from de-icing salts, or was going to suffer from de-icing salts, and they say substituted about 15 tonne of stainless steel reinforcing in it, about 5% of the total tonnage of reinforcement, added about 1% to the capital cost. Little graph, and these are the classic little graphs of time versus what you've got to do, looking at carbon steel, epoxy coated and stainless steel, and every time you have to do a service on either the epoxy coated or the carbon steel, the stainless steel wins even more and more. Now, that's a very, very simplistic model, and it assumed there was no damage to the epoxy coated on the way through, and they didn't look at galvanised at all. They just didn't think of it. Well, I'm not sure why they didn't. Chris will recognise this if he's still in the audience. Yes, yeah. Tasmania, he was heavily involved with this. It's GHD's little thing. This is a marine environment, clearly, and it has some selective use of stainless steel in it. Up here, carbon steel. Down below the water level, carbon steel. Concrete, high performance. Off-site, if you could, but there were some places where you couldn't. And so those places used stainless steel. Mind you, there was a bit of braces and belt and some additives as well, but it's a long, long life. And the McGee, he's the bloke in the Tasmanian board who were happy with stainless steel. Perhaps I should say he was interested in stainless steel. Gateway Bridge. This is the bridge that has 3 times the design life to its companion bridge. And so they said, right, well, we've got to use lots of stainless steel because otherwise it won't last. So in this area here, down around the tidal zone or where it may get hit, the bottom of the piers, so down the bottom here, it's all stainless steel reinforcement, absolutely, because of the possibility of getting chlorides in. So, I said before selective, yep, selective. Joints where chlorides could get in, water goes through, leaves the salts behind on the surface, joints again, same thing, joints. So you're replacing only the bits of stainless steel, bits of Rio in the area where they could get lots of chlorides easily, and that gives you an advantage. Whoops. And here's just a picture of stainless steel reinforcement near the surface, and deep inside, cheaper, large diameter, and stronger carbon steel. And finally, let's talk about the oldest reinforcement at all, of all. This is out of AS4312, looking at the amount of chlorides you get as you come in from the ocean. And if you're in a Melbourne Bay, then you're down here and you're a couple of 100 metres in and there's nothing there. If you're in Newcastle, which is there, you're 4, 5, 6 kilometres inland. Why does that matter? Well, if you have wind blowing in and the wind gets the chlorides into the inner brick wall, and then you have an earthquake, then things fall down. And it's because you're galvanised or perhaps just plain carbon steel brick ties just fell apart. So we now have an Australian standard, 2699, that says thou shalt use stainless steel in high chloride environments. And it's a reinforcement. It's not Rio in terms of concrete structures, but it's certainly using stainless steel in an appropriate environment.